So today we are gonna be answering some chemistry questions, and we're first gonna start with the equilibrium constant, or Kc. Our first problem is at a certain temperature, Kc, the equilibrium constant, is equal to 7.98 times 10 to the negative 2 for this equation. What are the concentrations for B and C when concentration of A is equal to 0.0566 moles per liter? So first we have to know that the formula for Kc is the concentration of products over the concentration of reactants. Here, in this equation, our products are going to be B and C. So if we follow the formula, it's just B and C over our concentration of A, but they tell us that A is equal to 0.0566. So, but since A has this coefficient in front, and it's a 2, we're just going to square this. So now, we are going to plug in x for both of them, for B and C, since we don't know what they are. We are trying to find that out. And when you square 0.0566, you get 0.0032. Okay, so we have this. We know that Kc is 7.98 times 10 to the negative 2. It's going to be equal to x squared over 0.0032. This is going to be equal to 7.98 times 10 to the negative 2 times 0.0032. It's going to equal x squared. So I did this, and when you multiply these two, you get 0.00026 equal to x2. So now you just get the square root of each, and we are left with x is equal to 1.6 times 10 to the negative 2, and x is going to be the concentration of B and the concentration of C, and that is our answer. Our second problem, is going to be still Kc. We're still trying to find Kc, and they give us this equation. A plus 3B equals 2Cl. It's 2C plus D. And concentrations of B equals 3.4 molar and D equals 1.2. The reason why they only give us D and B is because when it comes to the Kc when it comes down to equilibrium constant, we only take into consideration aqueous solutions and gas solutions. So this A is solid. So when it comes to Kc, we don't take it into consideration. And over here, in the product side, this is supposed to be liquid, but this C is liquid. Since it's not a gas or an aqueous, we don't take it into consideration. So when it comes down to writing our formula, our products is just going to be our D value, and our reactants is just going to be our B value, but it's going to be cubed since we have this uh, 3 in there. So it's going to be cubed. Now we just plug in the numbers that they give us. So it's going to be for D, 1.2 over B. They give us 3.4. So we're just going to put like 3.4, but cubed. So what does that give us? That gives us 1.2 over, when you multiply it, 39.304. And now all you simply do is divide it to get your KC value, which is going to be 0.031. And that is our KC value. So now we're moving from KC, the equilibrium constant, to rate, which is the rate at which an equation is happening. So our first problem is the composition of N2O5 is given by this equation, right? They give us this equation. If rate is equal to 7.50 times 10 to the negative 4, what is the half-life? Half-life. Assume it's first order. This is really important as it determines which formula we're going to use. So now we look into our formula chart and they tell us it's first order. So we're going to look at the half-life equation. This is the equation and that's what we're going to use. So for our half-life, we have to write it down, right? So it's our half-life equations is T equals to ln of 2 over K. This problem is really easy because we already have everything we need to know. And ln of 2, we can just put it like that in the calculator. So it's just ln of 2. We don't have to do anything. And K, they give us K. That's K. So we just plug it in. 7.50 times 10 to negative 4. We do that. We can just plug it just like this in our calculator, and we get 9.24 times 10 to the second power. That's our answer. So our next problem is calculate rate of water when CO2 is equal to 0.020 moles per second. And this is the composition formula. What we first have to do is balance this equation because this is not balanced. So we have to put an 8 here. We have to put a 5 here in order to balance it, and a 6 here. And this is now all balanced. When we are trying to find a rate like this, there is a certain step we have to do. And we have to write out the rate equation. So rate, and we have to write each coefficient for each of the molecules. So since here is just this, it's 1, it's going to be like 1 over 1. And then you have to put the delta of the concentration of C5H12 over delta time. And this is going to be equal, this is minus. It's going to be equal to the negative 1 over whatever this is. So it's 8 delta, the concentration of O2, equal to delta T is equal. Since this is our reactants, we always put a negative sign in here because we're losing reactants in order to make products. And since we have that, we are making products, these coefficients are gonna be positive. So it's gonna be 1 over 5, positive 1 over 5, delta the concentration of CO2 over delta time is equal. It's always equal to 1 over 6 because still we're products, delta concentration of H2O of water over time. So what do they give us? They give us the concentration of CO2. So we just bring this over here and we plug it in. We have 1 over 5 and we just substitute 0.020 into the concentration. So it's going to be 1 over 5, 0.020. And we are trying to find water. We all right now we're focusing on the water. So we just put this together and it's 1 over 5 times 0.020 is equal to 1 over 6, and water is going to be our x. This is what we are trying to find. So what do we do now? All we do is solve for this, which we get 0.004 is equal to 1 over 6x. We just solve for x, which is 0.004 times 6 is equal to x. X in this case is going to be equal to 0.0024 more percent. Easy, right? Now onto our last problem today. It is in a zero order reaction, the reactant depletes to 0.034 molar from 0.46 molar in 0.65 hours. What is the half-life for this reaction? So this problem has a two-step solution. All right, our first step is we go back to this formula, right? And remember how we used only half-life on the previous example? Well, now we have to use this integrated rate law in order to find this half-life. So since they tell us that it's a zero order, we're going to use this equation in order to find k. So then we can plug in k into this k, and this is how we're going to find time. They give us a time right now, but this is not our final time. We're trying to find the half-life. So we're going to have to use this equation. So we go back to our paper, and we use this equation. It is going to be AT minus A naught is equal to negative KT. Well, what do we know now? We know what's AT. We know what A naught is, and we know what our time in here is. So you notice how this is in hours. In order to plug it in here in this formula, we have to keep it in seconds. So what we're gonna do, simply, we're just gonna make this 0.65 hours into seconds. How do we do that? Is we just put it into this formula, hours. In 1 hour, there's 60 minutes. In 1 minute, we have 60 seconds, which is what we have. We multiply 0.65 times 60 times 60, and we get a total of 2,340 seconds. Saying that, we can now plug in this formula, which will be what did we say AT was? 0.034. So it's 0.034 molar. 0.034 we have minus our A naught, which is 0.46, over our 2,340 seconds. We do this, we solve for over here, and we get negative 0.426. When we divide what we found for our A naught, AT minus A naught, divided by our time, we're going to get our K. Our K is going to be 1.82 times 10 to the negative 4. All right, we got that. But this is only part one of our two-step solution. Our second step now is to go to our half-life equation, and now just plug in what we have. So this is our K. We're going to use our half-life equation to plug it in. A naught, it keeps being the same, 0.46 over 2 times 1.82 e negative 4. We do this, and we get a half-life of 1250 seconds, and that is our final answer.